Good morning, everyone. This morning we are going to talk about exponents. So the very first thing that you must understand is what is the definition of exponent? Another word we often use with this is the concept of power. And so if I put on the board something that looks like this, as you see, we have a big 3 here and a small letter and a small 4 right above it there. What does this mean? This number here is called the base. This number up here is called the exponent, also called the power. Okay, those two words are often used interchangeably. I just want you to understand, some of you that are older will have always heard the word power. Some of you younger ones may have only heard the word exponent. So they're used interchangeably. But what does this actually mean? And it's really important to understand what this means. This means that the base is repeated as a factor this many times. In other words, the power tells how many times the base is repeated as a factor. So this means 3 times 3 times 3 times 3. If they ask you for the exponent form of the answer, and it will say, give me the exponent, this is what they want right here. If they ask for the definition of the exponent, this is what they're going to want you to put down. What does it mean? If they ask for the decimal form of an answer, then you're going to multiply those 3's together and come up with the number 81. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So that's the definition of exponent with the 3 forms that they will ask for the answer. As you are working through these problems, you will find that sometimes they put the answer in this form when you're done. Sometimes they'll put it in this form. And you're sitting there going, why? Which one and why is it which one? As a general rule, what I have noticed is if your base is small and your power is small, then they will put it into decimal form. If your base is larger and your power is larger, and so the multiplication gets to be longer and longer, often they will leave it in exponential form. So you can kind of use that as you're working through your assignment to know what to do. Okay, next step. Now, there are definite rules that we work with when we are working with exponents. And that's what we're going to focus on mostly in this lecture, is these rules. The very first rule that we're going to look at is a product rule. Now, when you do the product rule, there are some definite things that have to be there. The first thing that has to be true is that it must use multiplication. If the connecting operation between your terms is not multiplication, then you may not apply the product rule. The second thing you have to have for the product rule to work is the same base. I'm going to give you some examples of these in a minute. If those two things are true, then what happens? 1, you keep that base and you add the exponents. So let's look at something so that you can see how that applies. Okay, so let's look at that. 3 to the 3rd power times 3 to the 4th power. First of all, let's check. Multiplication, yes. Same base, yes. Therefore, we can apply the rule, keep the base, which is 3, and add your exponents, which is 3 plus 4, which equals 3 to the 7th power. Okay, pretty straightforward, isn't it? But why is this true? And that's the thing that you need to understand is the why. Why is this true? Well, what is your definition of exponent? 3 to the third power means 3 times 3 times 3, correct? Yep, that's right. And now 3 to the fourth power is what? Tell me. Yeah, 3 times 3 times 3 times 3. You got it. Now, how many times is 3 used as a factor? How many repeated times? Count them. 1, 2, 3, 4, 5, 6, 7. You were right. It is 3 to the seventh power. Notice, they're exactly the same answer. Okay? So, if multiplication is your operation, your base is the same, you can add the exponents to get your answer. And here's the reason why. Okay, now you tell me. 2 to the second power plus 2 to the third power. Can I use the product rule on that? Yeah, you're right. No. Why can I not do it? Yeah, you're right. It's an addition. It's not a multiplication. So that's really important. If they gave you this, you would have to simply use your power here, your exponent, to say 2 times 2 is 4, plus 2 to the third power is 2 times 2 times 2, which is 8, which equals 12. That's all you could do with that. You could not apply any kind of product rule. Okay, now, next rule is going to be the quotient rule. And you're going to see some small differences in this thing, okay? First of all, with your quotient rule, you no longer have multiplication as the requirement. You will have something else, okay? So, what do you think the operation is going to be? If it's not multiplication, quotient indicates what? Yeah, you're right. It indicates division. So therefore, it must be division. Okay? Again, same thing applies. It's the same base. And then what is true? You're going to keep the base, but instead of adding the exponents, you're going to subtract the exponents. Okay? A little bit different, not quite the same. Okay, so now let's look at an example so we can see how this operates. Let's go 2 to the fourth power divided by 2 to the third power. Okay, let's see. Is it division? Yes, it is division. Is it the same base? You tell me. Yeah, the 2 is the base in both of these. Now, according to our rule, says we keep the base. That means 2 is written as your base. Subtract the exponents. The numerator is 4 minus the denominator exponent, which is 2. So that gives me 2 to the 2 power. 4 minus 2 is 2. Or we sometimes say 2 squared. But why is this true, guys? This is what's important to understand is the why. It's true because of your definition of exponent. Remember, the base is used as a factor 4 times. So 2 times 2 times 2 times 2 over 2 times 2. Well, 2 divided by 2 is 1. 2 divided by 2 is 1. And that leaves me 1 on the bottom, which doesn't change the top. So 2 times 2 is 2 squared. Or if we went to decimal, it would be 4. Although that's not what we're looking at right now. So 2 squared. That's exactly the same thing you get when you apply the rule. Okay? So that's why it is. Now, let's look at something else. What if I did something like this? 2 to the 2 over 2 to the 4. Now what do I have? This one's a little bit harder to figure out. If we do our subtraction of exponents like we were told to do, 2 minus 4 leads me to 2 to the negative 2 power. We can't leave an answer that way. And I'm going to go into this in a minute when we get to negative exponents. But whenever you have a negative exponent, it transposes to 1 over that base to the positive power that's this opposite of what you have. So it's 1 over 2 squared. But let's look at why this is true. Again, using your definition of exponents, 2 times 2 over 2 times 2 times 2 times 2. Again, 2 divided by 2 is 1, 2 divided by 2 is 1, leaving you 1 on top. So therefore, we have 1 over 2 squared. Exactly the same thing. Another way you could have treated this was to use your 2 squared on top, 2 to the 4th on bottom, and instead of doing the subtraction up there, we could have subtracted down here, making that a 1, and that gives you 1 over 2 to the 2nd power. We're going to actually use this form when we do a simplification of a much larger problem. So there it is, your quotient rule of exponents. Now, next thing we're going to look at is something called the zero rule and the exponent of zero rule. Zero exponent. What happens when we have a zero exponent? Anything to the 0 power is the number 1. And I know you're sitting there, do I have to memorize this? Are you kidding? Do I really got to memorize this? Yeah, I think you do. But I'm going to show you why it is in a minute. And this is going to lead to the negative exponent rule. And again, we're going to arrive by that by showing you the method that makes sense, okay? The negative exponent rule, and again, I already touched on that when I had 2 to the negative 2 is equal to 1 over 2 to the positive 2, okay? In general, this would be written as x to the 0 is equal to 1. This one would be written as x to the negative a is equal to 1 over x to the a. It doesn't matter what you use in those letters. It's the indication that we're looking for. So why is this true? Well, let's start with 2 to the 3rd power. That's pretty good. That equals 27. No, I'm thinking 3. We'll do 3. I started that way. Let's do 3. 3 to the 3rd power is equal to 27. Okay? 3 to the 2nd power is 3 times 3, which is 9. 3 to the 1st power is one of those 3's, and that's 3. Now let's look. What has happened as we have gone from here to here to here? Well, first of all, 27 divided by 3 is equal to 9. Is that correct? Yeah, you're right. Then 9 divided by 3 is equal to 3. So, moving down 3 to the 0 power, notice every time you descend one number, you get one number less on your exponent, you are dividing by 3 over here on the answer side. So 3 divided by 3 produces the number 1. Remember also that division by 3 is the same as multiplication by 1/3. And we're going to use that one in this next one now. 3 to the negative 1 power, what does that equal to? Okay, remember division by 3 is the same as multiplication by 1/3. So we're going to multiply that 1 by 1/3. Maybe use a dot instead of that. Multiplication by 1/3. 1 times 1/3 is 1 over 3. And remember, 3 is also the same as 3 to the 1st power. Look, the negative became a positive when it did that change. But this is why that's happening. Let's do one more. Let's do 3 to the negative 2. Again, that's going to be a multiplication by 1/3. Okay, well, this is going to be 1 over, because 1 times 1 is 1. And we're going to keep the 3's in exponential form, so it's 3 times 3, which is the same as 1 over 3 to the second power. Okay, notice negative became positive. And it's because of that factor that I tell people that a negative exponent on a base makes a position changer. It is going to change that particular base from where it is in the division form to the other position. In other words, from the numerator to the denominator. And the same thing is true if it's in the denominator, it's going to change its position to the numerator. So let's look at that a little bit more. So if I have x to the negative 1 over y to the negative 2, if we're going to apply that position changer rule, here's my division bar. My x to the negative 1, to make it positive, has to go to the bottom. My y to the negative 2 that is on the bottom has to move to the top to make it y squared. That is that negative exponent rule carried all the way out to its final completion, is that it goes all the way to wherever it is. Top goes to the bottom, bottom goes to the top. Okay? Any questions on that? That might be one you might want to ask more about because it's a little bit more complex. Okay, next step is the power rules. Okay, and these come in various formats. Okay, first power rule. 6, and we're going to put power rules up here. And I think I'll use letters this time because that's kind of what they like anyhow. Okay. Let's see. Let's go 4 to get a number first. 4x to the, we're going to do numbers. It's easier. 2y to the third. And let's raise this to the second power. Okay, that's one form of the power rule. We'll go through it first. Okay, so this power rule says I'm raising this whole thing inside the parentheses to another power. And I usually call these a power to power. Why? Look at it. I have a power here and another power there. That's why I call them power to power. I'm going from one power to another power. Well, what does this mean? First of all, this 2 here says this whole thing is multiplied times itself twice. So 4x squared y cubed times 4x squared y cubed. If we do that, now we can use our product rule, which we already know about. 4 times 4, which is 4 squared. X squared times x squared, same base, keep it. Add the exponents. And then y cubed times y cubed, keep your base, add your exponents, okay? Now, that's not the shortcut though. That's not the actual rule. That's the explanation of the rule. The rule is that you keep the base and you multiply the exponent of each one of these bases times the exponent outside. So this would be 4 to the 1 times 2, x to the 2 times 2, and y to the 3 times 2, which equals 4 to the second power, x to the 4th power, and y to the 6th power. Is that not what we got by using the other method? It sure is. So that's your first form of the power rule, when it's just simply a multiplication inside raised to another power on the outside. Okay? Now, what's the next form of the power rule? This is the form where you now have a fraction form. You have like 2x to the third over y to the 4th, raise this whole thing to the 5th power. Okay, now you've kind of been introduced to that rule where you know if you've got powers inside and a power outside, you're going to multiply those exponents. You're right. So this would be, since it's 2 to the 1st, even though we don't write it, it would be 2 to the 1 times 5, and then x to the 3 times 5 over y to the 4 times 5, which is going to equal 2 to the 5th, x to the 15th, and y to the 20th. Now, we could go back to the definition and write this down 5 times like we did the first one, but that gets pretty long. But you can use that to get there. So the power rule is you take the power that's with your base, multiply it times the power outside. The power with the base, multiply it times the power outside. The power with the base, multiply it times the power outside. And that's what happens on a power to power rule. Okay? So that's the 2 basic forms of that power rule. Okay, we're going to look at one more kind of it though. We're actually going to look at where we have a negative power. So let's look at that. 2 to the 2, x to the 4 over y to the 3rd. And we're going to raise that to the negative 2 power. There's various ways you can work with this. Remember that negative power did what when we looked at it earlier? It changed the position of what it deals with. So, if we were to apply this, we could say 2 to the 2nd, x to the 4th to the negative 2 power over y to the 3rd. Oh, let's get that written clearer. There we go, 3rd to the negative 2 power. Now we have a negative power and a negative power. This negative power can change the position of everything it covers. So this is 2 squared x to the 4th to the 2nd power, and this one would be y cubed, and now to the 2nd power. See how that changed the position? So we could say that a negative exponent outside forces a reciprocal of what is inside. Do you see that? This changed position to this. And so we could have written this as simply this. Y cubed over 2 squared x to the 4th to the 2nd power. You see how that flipped its position, took the reciprocal of everything? And now you can apply your power rule and get y to the 6th over 2 to the 2 times 2 is 4, and x to the 8th. Okay? So that's one way to approach this. When you're getting into these kind of rules where we're dealing with power rules and it gets more and more complex, there's a lot of different orders that you can do this with. It doesn't always follow exactly the same thing, although you can always follow, but there's many different pathways. So just because this pathway is different from another one that you have learned does not mean that the one you have learned is incorrect, because there are many pathways. So we're going to move now to a very complex kind of a problem. And we're going to look at the order that we might want to do this problem in, okay? So let's look at this. Okay. We have here two things happening. I'm going to put it closer to the middle. We have 3x squared over y times 4x cubed over y to the negative 2, and this is raised to the negative 1 power. Okay, when I am dealing with things like this, the first thing I am going to do is apply the power to power rules. So that's my first step, apply power rules. Okay, my first one doesn't have a power rule. My second one does. So I'm going to first of all apply that power rule. And I can either apply it by flipping it, or I can apply it by using the multiplication of the power. And I'm going to do the multiplication of the power first. So this becomes the same as it is, 3x squared over y times, and I'm going to multiply 1 times negative 1 is 4 to the negative 1, and x to the negative 3, because it's 3 times negative 1, over y. Negative 2 times negative 1 is a positive 2. Okay? Now, the next thing I'm going to do is eliminate this multiplication by putting everything on top together and everything on bottom together. Nah. No, I'm going to make, the second thing I'm going to do is make all negative exponents positive. And remember how to do that. You do it by changing the position of where it's at. Okay? As I told you, there's many routes to do on this, but we're going to go the route of making all negative exponents positive. Okay, this one doesn't have any negative exponents, so it's going to stay the same. And I'm also going to put it into one long thing. 4 to the negative 1 makes the 4 go to the bottom. X to the negative 3 makes that go to the bottom and become a positive 3. And y is still here, and y squared. Don't forget that. We have a y from here and a y squared from there. Okay? Now, everything's on top, everything's on bottom. Now, my next step is to look at combining, and if there's more than one same base in the numerator or same base in the denominator, I'm going to make those become one part. So this is going to be the application of the product rule. So we're going to apply the product rule. Okay? In the numerator, there's no product rule to be applied because we only have 3x squared. None of that is the same base. On the bottom, though, we have 4. We have x cubed, and we have y to the first times y to the second, which means y to the 1 plus 2, which is 3. Okay, so we applied that product rule. Now, my last step is going to be to apply my quotient rule. Okay? So we will apply the quotient rule. Okay? Do we have the same base in the numerator and the denominator? Yes, we do. We have x's here. The exponent in the numerator is smaller than the exponent in the denominator. Therefore, I am going to do my subtraction in the denominator. So we're going to have 3, and the x squared on top is going to become a 1, because x squared divided by x squared is 1. And you have 4 times x to the 3 minus 2, because that's also divided by that x squared. So there is my division, and then my y cubed that doesn't change. And this finally ends up with 3 times 1 is 3 over 4 times x to the 3 minus 2 is just simply x, and then y to the third. And notice, whenever we have 1 as an exponent, we usually do not write it. But as you will notice, I sometimes write it to help us know what we're adding on our exponents. Okay, I think that does it. Go and apply it. It's hard work. Oh, I could give you one more. Let me do one more that's going to be a little bit harder, and you'll see how these rules work again. I think that'll be good. One more problem that's a little bit harder, that you really see the use of these rules. Okay, let's look at this. Negative 4 m to the 5th times n to the 4th over 24 m n to the negative 7. This whole thing is going to be raised to the negative 2 power. Okay, looking at those order of our rules. Order of the rules says apply the power rule first. Remember, that's to the first and that's to the first. And this is a negative 4 in parentheses. We have to remember that whole thing goes, okay? So, applying those rules, it goes first to the power rules. So I have a negative 4 raised to the 1 times negative 2 is a negative 2 power. 5 times negative 2 is a negative 10. And n, 4 times negative 2 is a negative 8. All of which is over 24 to the first power. Well, 1 times negative 2, again, is a negative 2. 1 times negative 2 is a negative 2. And n, negative 7 times negative 2 is a positive 14. Okay? So we applied the power rules. Our next step now is to make all negative exponents positive. Let's identify them. This one, this one, this one all have negative exponents, and this one and this one. So looking at that, let's go down. 4 is going to end up on the bottom. A negative 4 squared, well, let's change that to 16 because it's going to become negative 4 times negative 4 is a positive 16, and it's going to go to the bottom. M to the 10th, negative 10, comes down and becomes m to the 10th. N to the negative 8 comes down and becomes n to the 8th. See how they went from numerator to denominator? Okay, now looking at the denominator, 24 to the negative 2, I'm going to leave it as 24 squared. Okay, and then we have m to the negative 2 comes to the top and becomes m to the second. And n to the 14, because it's a positive, stays on the bottom. So, did we make all the exponents positive? Yes, we did. Every single one of these negative exponents is now a positive exponent. All right? Next step says apply the product rule. Remember, product rule says same base as a multiplication. No same bases on top, but on the bottom, we have these two have the same base. So that's going to be the product rule applied there. 24 squared, m squared over 16, m to the 10, and n to the 8 plus 14 makes the 22nd power. All right? Now, our last step says apply the quotient rule. Okay, quotient rule is going to be the same base in the numerator and the denominator. So we have m squared and m to the 10th. Where is my larger exponent, the top or the bottom? Yes, it's in the bottom or the denominator. So that is where my subtraction is going to take place. So you're going to have 24 squared, and then on the bottom, you're going to have 16 m to the 10 minus 2, and then n to the 22nd. Simplifying that farther. 24 squared is a pretty big number. But remember, 24 can be written as 4 times 6, right? I'm going to drop this one back to 4 squared. You're going to see why in a minute. So 24 squared is 4 times 6 squared, which means 4 squared times 6 squared, right? Because this is to the first, 1 times 2 is 2, and 1 times 2 is 2. This is going to help our simplification. So we're going to have 4 squared times 6 squared on top over 4 squared. We're going to simplify this, have m to the 8 and n to the 22nd. Why did I do that? Notice, 4 squared over 4 squared. 4 squared divided by 4 squared is 1. So I'm left with 6 squared, which is 36, over m to the 8 and n to the 22nd. Okay, you see how you apply those rules? First of all, apply the power rules. Second, make all negative exponents positive, which happened from here to here, and then applied the product rule, where we had 2 of them with the same base in the same level, and so that became your n to the 22nd. Came down here and said, okay, we can start working on that quotient rule, but we actually are going to have another one because of 24 and 4 squared. So we put 16 back to 4 squared and looked at 24 as the product of 4 times 6. And that brought to the power, bringing 4 squared times 6 squared. That permitted our 4 squareds to cancel each other out, becoming 1 and 1. And so therefore I'm left with 36 on top over m to the 8th and n to the 22nd on the bottom. As you see, if you have a system, it helps keep you on track. But again, this is not the only system you could use. You could use many different orders of system as long as what you're doing applies accurately the power rules, the exponent rules for negatives, and the product rule and the quotient rule. The order of these are not as particular as they are in many other things. Okay, good luck and good work.